we deal with natural numbers in general, unless if they give you a certain condition. So meaning that any question that we're given that we're going to be using the predicate Pn, always, if they didn't tell you anything about the statement, you're always going to assume that n is an element of a natural number, right? Meaning that you're going to plug P1 to confirm if the first part is correct, right? Unless if they tell you that n is greater than 3 or n is greater than 0 or anything greater or 0, anything, doesn't matter what they give you. But initially, we should always know that a natural number is the default number that we're going to use, or default numbers that we're going to use for this. So without any waste of time, I'm going to come to this statement so that we can know that the medical induction is based on what type of a predicate, right? And what is the reason for this. So if we come to medical induction, we know that we're going to be using a conditional statement. Conditional statement says that if P, then Q. You see, right? It says if P, then Q. So we're going to have a statement first to, let's say I let a predicate, and this predicate is under the field of natural numbers. After picking this statement and checking that indeed this is true, we're going to use if, then we conclude our statement from there, right? So we're going to assume that if P of K is true, then P of K plus 1 is also true, which means that this weight is very important and this is very important. You see, right? So this is always the case. Every time when you're solving a statement or a question, you are always going to let P of n be a predicate on the set of natural numbers, satisfying whatever statement you're dealing with. So for what you're going to be doing here, we're going to say let Pn be the statement. It's going to be this statement, whatever that you're given, you're going to copy all of it. So also this can be replaced by saying P of n such that then you write all this statement here. You see, right? This statement. So we are letting a predicate first. The reason why we are letting a predicate first is because you're going to be dealing with these truth values, a true and a false. You see, right? We're going to be dealing with these two truth values. You see, right? So that's why we're letting a predicate. So if we look at the first example, we are given this. They say that use the principle of mathematical induction, meaning that we should use PMI, right? The principle of mathematical induction, PMI, right? Then they say to prove that this is also that for all n element of natural numbers. So first thing they did what? They let P of n, which this has a mark, right? Let P of n be the statement. You let it be that statement. Copy all of it, including this. And then, when you check, your natural numbers start from 1. That's why when we come here, we're going to plug 1. We plug a 1. It's like we're in a number plane, right? We plug a 1. Let's say we're saying that this starts from 1. We plug a 1. If we want to move to another number, we can randomly, since we want to move to the second one, we can say it's possible to move to a 1, 2, 3, but then we're interested in a number that is random. K can be 2, K can be 3, K can be 4. You see that, and it can also be 1. So we're saying that now we're going to assume that P of K is true. Then we say IE, then we copy the statement, we replace n by K. We say for sum. Now we're going to say for sum. You see, right? K element of a natural number. So meaning that it should also satisfy the same field as n, but for some, not for all, right? Then we are saying that it's possible that the next number here may be K plus 1. The next number after this one. That's why we are saying that next we must say that if this is true, it means that the second number will also be true after that one. You say if K is 1, it means that 2 will be true. If K is 2, 3 will be 2. This is what this statement is saying. You say, right? Then we're going to deduce that P of K is also true. This is what we're interested in. So on the statement of assuming, they are more interested on this one. On the statement of deducing, they are more interested in the word also true, right? Then we need to deduce this, right? Then we're going to say i.e. Now, since remember, since here we're dealing with this, let me erase whatever I've been writing before here. Then I explain this part. Since we're dealing with a sequence here, right? You can see this is a sequence. You can see dot, 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 and then plus, you continue. That's a sequence. Since we're dealing with a sequence, every time we come to the deducing part, we first copy the assumption, the left-hand side of the assumption. Then we replace k, we replace that k by k plus 1. You see, right? Then we say equals to that. The right-hand side, we don't change anything, we just replace by k plus 1. Then, if we can take this, it will always be the same. Let's go to an example that is similar to this. I want to show you something. Unless if we don't have that example, we can just look at a tutorial. You see this one, right? If I come and assume that k is true for some, this would be k, right? And this would be k. But when I come to deduce, I'm going to copy this entire thing, then I say plus, then I copy this and then replace k plus 1 by, you replace k by k plus 1. You see right now, mean that this will be 2k plus 1 minus 1. And this will be equals to k plus 1 squared. The right hand side, we don't copy anything, we just take this, replace by k plus 1. You see right? On the left hand side, always, whenever you're deducing and it's a sequence you see by those dots, you're always going to make sure that you keep the assumption as it is, you add, then you take this, replace k by k plus 1. You see right? So this is always going to be the same. Now, let's go back to that question, right? Since we replaced k by k plus 1 after copying the assumption, now we come and say that we're going to pick the left-hand side. If you check here, we pick the left-hand side, right, as it is. After picking the left-hand side, we surely know that this is the same as this. So we plug k plus your k squared into k plus 1 or squared over 4. We said it. Then we realize something, that they have something in common. K to the 2, k plus 1 to the 2. You see, then I factor it out. But here, after substituting your assumption, you need to give these reasons writing by assumption, right? You're going to write by assumption after substituting your assumption. Then, from there, you're going to factor out the common fact. This is always the case. You'll see when we're going to do those tutorials, you always factor out the common factor after substituting your assumption. You factor out the common factor, then you simplify the inside. When I simplify the inside, I'm going to get this. Because here I'm going to take this, multiply by 4, then I add it to k squared. You see, right? You know how, I'm sure you know how to simplify this. Then, after simplifying this, I can factor the numerator. Factorize the numerator, I get k plus 2, and that is k squared. K plus 2 all squared. Then it's indeed equals to the right hand side. You see, right? But it's more simpler when you summarize this right hand side, so that you know what it is that you're going to get. Then, since you say that this is equal to the right hand side, you're going to come here and say thus p of k plus 1, because you were proving p of k plus 1 here right now, is also true. Then you come and say hence p of n. Now you prove the predicate, you deduce the predicate is true for all n element of a natural number, and that it is right now. That's what you get. Then that conclusion may have a lot of marks. You can see it right now. Thus p of k plus 1 is also true. Hence p of n is true for all n element of a natural number. Now let's go to the tutorial based on this question. Yeah, here's the first question, right? If we check, we're given this question first. What you're going to do first, you're going to let p of n be the statement, and then you write the statement. You say right, or maybe you let p of n such that, which is still the same thing. You say right, let p of n be the statement, Then you copy that into a statement. Then after copying that into a statement, we realize that our n starts from 1. So we're going to plug 1 there. Then we get 1. Let's check. This is the left hand side, right? Which is this one. The right hand side is this one, n squared, which you get 1. So if you check, these two are equal. Hence, P of 1 is true. You say right. Then, now we assume that P of n, your P of k is true for some k element of n. Since here is an element of n, we're just going to replace by this. If this was an element, if here they had said n greater or equals to 1, even here we're going to say that k greater or equals to 1. You see, this one should always match here. I'm sure you see right. Then we replace n by k. Now after replacing n by k, we're going to deduce that P of k plus 1 is also true. This statement is very important. Also, you can see I've underlined, I've circled this right now. It's also true. Then we're going to copy the entire assumption, the left hand side of the assumption. I'm sure you see this. We copy the left hand side of the assumption. We paste it there. Then we come and copy this last one, and then replace k by k plus 1. You see right? So this is how the deducing part will always be. Then this will be equals to k plus 1 all squared. Remember, if I replace this by k plus 1, to be k plus 1 all squared. Then from here, I can pick the left hand side. Right? If I pick the left hand side, this is the left hand side. Remember, this one is equal to the assumption, which is equal to k squared. So I can plug k squared there, replace it by k squared. Then I say from assumption. Remember I said that these reasons are very important. And remember I said that most of them here, after this step of substituting k squared, you have to factor out. But here there's nothing to factor out. So we just have to simplify this, which is the same thing as k plus 1 all squared, which is equal to the right hand side. You see right? I should have even written here also right hand side. Hence, or thus, P of k plus 1 is also true. Hence, P of n is true for all n element of a natural number. I'm sure we see this, right? Then, let's come to the second question. The second question, we're given a similar scenario, right? They said this is equal to the right hand side, right? Let's say for all n elements of a natural number. Then we're going to do the same thing. We'll let P of n. Let's go let P of n. Such that, remember I said that it's also fine. If you don't want to let P of n be the statement, you can just say such that, right? And then you say 1 squared plus 2 squared plus 3 squared. Then this shows that this is a sequence. It means that when we come to the assumption, we're going to, after assumption, going to the deducing part, we're going to copy this assumption. Then we take this last one, we edit here, and then we replace k by k plus 1. You see, right? This is what we're always going to do with the sequence. So let's look at this. We let P of n be the statement such that n is an element of a natural number. Then we know natural numbers start from 1. So we plug 1 on the left hand side, we get 1. So always, guys, when we plug a 1, or when we plug the first number here, we are going to ignore all the numbers on the left hand side. We consider the one which has n only. You see, right? Then on the right hand side, we'll also consider the one which has n, which is always the case. Then we have n. Then here on the right hand side, we get 1. Now, we see that hence P of 1 is true. Now we come to assume that P of n is true for some. Remember, this statement is very important. This is equal to the right hand side. We just replace n by k. Now we come to deducing. We say that also is very important. You see, right? Then we copy the entire assumption here. Then we add k plus 1 all squared based on this last one. And then the right hand side, we just replace k by k plus 1. We don't change anything. Then we get this. Then we pick the left hand side. Remember, from the left hand side, this is coming from the assumption. So we're going to replace it by this. Then we say from assumption. right? Let's go check. Then we replace it by this. Then we say from assumption. Now, after saying from assumption, we realize that there are some common factors that we see here, which is this and this, just that it's to the exponent 1. Then we factor it out. Then we're left with this, right? Then we simplify them. We say k plus 1 times 6, then we add it with this one, which we get this, right? Then we also simplify this one, which is 2k squared plus k. Then when we simplify further, we get this 2 is going to give us 7k. And these are brackets. It's going to give us a 6 times k plus k. It's going to give us 7k, right? Then plus 6. Then 7k, when we factor out, we get this. And this is the same thing as the right hand side. Let's go check the right hand side. The right hand side was k plus 1, k plus 2, 2k plus 3 all over 6, which is that k plus 1, k plus 2, 2k plus 3 all over 6. Thus, p of 1 is also true. Hence, p of n is true for all n elements of a natural number. I'm sure we see this, right? Then, here, the most important one to look at is the one of from assumption. This one of factoring out here. You can still tell them that you're factoring out a common factor of k plus 1, which is still fine. But this is the most important one. So this reasoning is very important. This one, you must give a reason from assumption. Then let's come to this one. Also a similar situation. Yeah, if we look at this, now they let p of n such that, we let p of n such that this is also this for all n element of natural number. You see, right? This won't change anything as long as it's a sequence. It won't change anything. When we come to p of 1, since n starts from 1, when we come to p of 1, we're going to plug 1 here only. Here, you see right now. When you plug 1, we get 2. Then on the right hand side, when we plug 1, we also get 2. So hence p of 1 is true for, we can just say it's true actually, for n equals 1, but we don't have to say that. Now, we assume that p of k is true for some k element of a natural number. Now, after assuming this, we just copy this entire thing, we replace n by k. You see, right? But remember what's very important here, it's saying for some k element of a natural number. Now, when we come to deducing, we say it's true, it's also true. Then we copy the left hand side of the assumption. You remember here, right? Then we take this thing, we edit here, we replace k by k plus 1. I'm sure you see this. If I replace this k by k plus 1, I get this. And if I replace this k by k plus 1, I get this, which is going to be equal to the right hand side. Then we simplify the right hand side to give us k plus 1, k plus 2, k plus 3 all over 3. Then we pick the left hand side. We remember that this is coming from the assumption. So we're going to replace it by this. You see, right? And then, after replacing it by that, okay, we're here. After replacing it by that, we realize that these are common factors. So we can factor them out after writing our reasoning from assumption, right? Then we factor those out. Here we're going to be left with k over 3, which is this. Plus, here we're left with 1. Then when we add these two, we're going to get k plus 3 all over 3. Then this is the right hand side. Remember, say that you can also write equals to the right hand side. Thus, p of 1 is true, it's also true. Hence, p of n is true for all n element of a natural number. I'm sure you can see that this is not difficult. The reasoning in most of the times is the same. You're just doing the same thing in different questions. So if they bring you a question like this, it won't be difficult. The only different question here would be when it has a factorial, which is the question that we'll be going to, right? If we look at D, they say let p of n then we copy that entire statement for all n elements of a natural number. That's the statement they gave us from the beginning. You see, right? Then from here, we plug 1. When we plug 1, we get 1 over 2. On the right hand side, we also get 1 over 2. Hence, P of 1 is true. Then when we say we assume K, P of K is true for some K element of a natural number. Remember, for some is very important. Then we're going to take this entire thing. We replace n by K. You see, right? Which is that. We'll replace n by K. Then when we come to P of K plus 1, we take this left part, which is this. Then we take this left part, right? Then we take this. Well, we edit here, we replace K by K plus 1. We take this, we edit here, we replace K by K plus 1. If I replace this K by K plus 1 here, I'm going to get K plus 2. You see, right? Then equals to the right hand side. I just replace K by K plus 1 here. I get K plus 2. Then I take the left hand side. After taking the left hand side, we remember that this is coming from the assumption. I believe that from there to here, it's very simple, right? You substitute, you say from assumption. But remember, I said that in most cases, after substituting from assumption, you need to factor out something. And it can only be factorized within these two, because this one is there. This one already we know we need it. It's there. You see, right? The only thing which we need to manipulate is this 2 to give us this. So we're going to use the law of factorials. We're going to expand this. We always expand the bigger one. We expand K plus 1 plus 2 to K plus 2 K plus 1 factorial. The reason being is because here already we have K plus 1, so we need them to be the same so that we can factor out, right? So we factor out that. We factor out, let's say after expanding this, we're going to factor out this 2 with the negative, because we need the negative in the final solution. You see, right? Then we factor out this with the negative. This sign will change to a negative inside. So we'll be left here with 1. Here we'll be left with minus this. K plus 1 over K plus 2. Then we simplify it. If we multiply this 2, we get K plus 2 minus K plus 1. Then you get this. Yes, sir. When you minus, remember after multiplying this here, you're going to get K plus 2 minus. Make sure that those are inside the bracket. As long as there are two things, make sure they're inside the bracket so that you can get this. You see, right? Then from here, these are going to disappear. These two are going to cancel each other. Then 2 minus 1 gives you 1. You see, right? Then from this part, we can put back this 1 times 1 is 1. Then this times this, you put the one without a factorial first, which is K plus 1. You put it here first. Then remember this, we had it from the beginning. This is the same thing as K plus 2 factorial. You see, right? Then we arrive to the right hand side. We could easily have said this is equal to the right hand side. You see, right? Thus P of K plus 1 is also true. Hence P of n is true for all n element of a natural number. Any question here? Is there any question? If there's no question, it means that we are moving along, right? Now we come to this question, which is E. This is also factorials, you see right there. So I'm gonna just skip this one for now. I'm gonna leave it to you to prove this one, which is E, right? You can see the solutions that you have them for E. F is also for factorials. I'm gonna leave it to you to solve this one. You can see the solutions, I have them here. So E and F, I'm gonna leave it to you to solve. Now let's go and look at the other part, the other kind of questions, right? Now we have this of divisibility. So they can say it's divisible by, or it's a multiple of, they can say in 2 ways, right? Now they tell you, use PMI to prove that 7 to the n plus 2 plus 8 to the 2n plus 1 is divisible by 57. for every non-negative integer. Remember, sometimes it's possible for this to start from 0. You see, right? Which is like that. Now, they do this. From here, we have this. We have that. We're going to let P of n be the statement such that we copy that entire statement. You see, right? We can even come here and see, like they gave it to us. You see, right? Then we start plugging 0 because this is starting from 0. If I plug 0 here, I get 57, and the condition is divisible by 57. You see, right? Now we see that indeed 57 is divisible by 57, hence P of 0 is true. You must always write this, which is divisible. As long as you're on these ones of divisible or multiple of, must write it's a multiple of, which is divisible by. Now, we do this. From here, we assume that P of k is true for some k. Remember I said that here if they say n greater or equal to 0, you must come and say k greater or equal to 0. You see, right? Then we copy this. We replace k by, you replace n by k. Then we're going to say this is equals to, and we're not going to say it's divisible by. We're going to write this in mathematical form after assuming. You see, right? This is equals to 57p. For p an element of an integer and k greater or equal to 0. Now we come and from there, this one of divisibility, guys, we are always, after letting this be equal to 57p, you're always going to let something be subject to the formula here. So we're going to pick this for the time being, right? 7 to the k plus 2 to be equal to this. Then we come to deduce. You'll see, when we pick the left hand side, we'll need to substitute something like that. You'll see that, right? From assumption. Then now we deduce that P of k plus 1 is also true. This word is very important. Then we copy this, will replace k by k plus 1, which is equal to, we simplify it, we get k 7 to the k plus 3 plus 8 to the 2k plus 3, which is equal to 57r. We're no longer going to choose the same variable because we've used that one. And you can't use k here and k here. You see, right? They must be different. Then we say for r element of an integer. Now we pick the left hand side. Remember here, we're no longer dealing with sequences. So we're going to take the assumption as it is. We replace k by k plus 1. Now from here, we see that if we pick the left hand side, we have to simplify any of these to give us this. Let me erase everything so that you can easily see what I'm highlighting. We have to simplify this to give us this. So we're going to separate 3 and a 2 there. Then we drop the 1. Then this one, we can substitute. This is equal to 57p minus 8. I should have said k. They should have said k here. It's a mistake, right? Minus 8 to the 2k plus 1. Then we multiply this 7 there. 7 times 57, we get 399p. Minus 7, these ones are not the same, so we can't multiply them. We just keep the 7 there. Plus 64, this. So here we just also separated this to be the same as this one. You see, right? Then we drop the 2. The 2 is 64. And then from here, we have a common fact. That's why we also, so in other words, these two must always make sure that we separate them to be the same as those ones there. These ones. Must make sure we separate them to be the same as this. You'll see when we come to the next questions, right? Now, we have a common factor here. We factor it out. When we factor it out, here we're going to have minus 7 plus 64. What is minus 7 plus 64? It's going to give us 57. You see, right? It's going to give us 57. And then from here we can factor out the 57 in both sides. here and here. Factor out the 57, then we get this. With R, make sure that when you replace this one inside. We have learned this in methods of proofs, that after factoring something that I'm looking for, I can replace whatever that is inside the brackets by some variable. So we're always going to replace by the one we chose here, because we're trying to prove that this y equal. With R being equal to this, which is an element of any integer. Then we say thus P of k is also true, hence P of n is true for all n greater or equal to 0. Now let's do this. Let's come to a question which is more like this. Now let's come here. We come to this question, right, which is in that man. They told us that 5 to the n minus 4n minus 1 is divisible by 16 for all n element of a natural number. Then now we're going to come and let P of n be the statement. Then we say we copy the statement, all of it, right? Then after copying that entire statement, we start plugging the first number, which is 1. If we plug 1, we get 0, which is divisible by 16. 0 is indeed divisible by 16. 0 divided by 16, we get 0. There's no remainder, right? Hence, P of 1 is true. Then we assume that P of k is true for some k element of a natural number. Then, this is true for some k element of a natural number. Then we copy that question, which was 5. Now we replace n by k. We say 5 to the n minus 4k minus 1, which is equal to 16. If they say it's divisible by 16, we say which is equal to 16 for p, which is equal to 16p for p element of an integer. Then I said that we must make one thing subject to the formula here, so we'll make 5 to the k subject to the formula. You see, right? Then we deduce that this is also true, P of k plus 1. Then we replace the k by k plus 1. Then we say it's equal to 16r for r element of an integer. Then, did I just say for r element of an integer only? Yeah, it's fine here. Then here, we're going to say this. We're going to say, after replacing this, k plus 1, we're going to pick the left hand side. Remember, after picking the left hand side, you must make sure you simplify this to be the same as this. You simplify this one after picking the left hand side to be the same as this one, so you can plug this side. You say, right? Then we're going to do that. So we're going to simplify this one to be the same as this. Then when we simplify it, we drop the 1. We get this, you see. Then we substitute that. This is from assumption. You see, right? Then we multiply by 5 everything. After multiplying by 5 everything, then we simplify. This is going to give us 16. The 5 will cancel the 5. So we'll have 80p plus 16k. Then we factor out 16. Then we get 5p plus 1. Then we replace this by r. Remember, we're dealing with r from the beginning. We picked r. So replace this by r with r an element of that, which is an element of k element of an integer. Remember, this is k. Alright. So this is very important also to say an element of an integer after replacing with r equals to this. Thus, P of k plus 1 is also true, hence P of n is true for all element of a natural number. Right? Now, if we check this one is also similar, now that tells us that this is divisible by 21. So that's what we're going to be doing now. We're going to look at the question. So we come, let P of n be, or let P of n such that we copy this entire statement. Then we start by plugging 1. Remember, it's 1 that we say, right? First, it's 1 here, n starts from 1. And then we plug 1 there, we get 21, which is divisible by 21. Did I write 16? 21. This is divisible by 21. I think my mind was still on the previous question. Which is divisible by 21. You say, right, hence P of 1 is true. Then when you come here and assume P of k is true for some k element of a natural number, remember this is very important, right? For some k element of a natural number, then we're going to take this entire question. We replace n by k, then we say equals to 21p for p element of a natural p element of an integer. Then we make something subject to the formula. Remember I said that you can make one thing here, so make this one subject to the formula. You see, right? After making that subject to the formula, we're going to deduce. We deduce that p of k plus 1 is also true. Then we take this k, we replace it by k plus 1. Take also this k, replace it by k plus 1. If you can see, it's like that, right? Which is equal to 21r now, instead of 21p, which is a different variable. Now, we pick the left-hand side. When we pick the left-hand side, on the left-hand side, yeah, sure, it's fine, I simplified it this. This is how you pick the left-hand side, right? You're going to say this, the left-hand side. Then you drop this. Again, you're trying to change this to be the same as this and this. You see, right? Meaning, on this one, I just need to drop the 1, which will be 4 to the exponent 1. Plus, there I have 2k minus 1, right? Then I'm going to say here 2k plus 1 minus 1. So if I multiply them here, 2k plus 1, 2k plus 2, if I simplify this, I'm going to get 2k plus 2 minus 1. This is going to give us 1. That's why here we got 2k plus 1. You see, right? And then from here, we realize that we need this thing to be the same as 2k minus 1. So we're going to simplify it. So this one, if we substitute this here, we get this from assumption, right? And then we multiply the 4. Multiply the 4, we get this 84 and this, right? So if we still want to make these two to be the same, you see now they're not the same. It's either you manipulate this one or this one. It's up to you which one to manipulate, or you manipulate both. You see, I just decided to drop this and I drop this so that they can be the same. See, now they're the same, right? Can manipulate in many ways. Then I factor out them because they're the same, right? Factor out this, yeah, I'll just be left with 5. Yeah, I'll be left with negative 4 over 5. So if I add negative 4 over 5 plus 5, I get 21 over 5, right? To the times 5 to the 2k. Then I now do this here. I factor out the 21. And here, when I factor out 21, here I'll be left with 4p, here I'll be left with 1 over 5 times this. Then I replace that by r, which is equals to 21r with r equals to that. You see, right? Thus, P of k is also true, hence P of n is true for all n elements of natural number. So, I'm sure we see that it's not that difficult to work with, right? Now this is also a similar case. Now they're saying that n squared plus n is even for all n elements of a natural number. So we know that this is starting from 1. So we're gonna pick 1, we get a 2. Is 2 even? Yes. So we will write which is even. You see, right? And then 2 is even. Then we say hence P of 1 is true. Then we come and assume P of k is true for some k element of a natural number. Then we replace n by k. We replace n by k. So we replace n by k, which is equal to 2p for p element of an integer, right? Then we make one thing with the formula. As long as we're still on these ones, we're always going to make one thing with the formula. We make k squared with the formula, we get this. Now we deduce. We take this, we replace k by k plus 1 take this, we replace k by k plus 1, which is equals to 2r for r element of an integer. Right? Then from here we pick the left hand side. When we pick the left hand side, we just simplified this one. Yourself, you're not going to simplify when you take the left hand side. That I was trying to summarize things. So you take the left hand side, that this is the same thing as this, is right? I just simplified it or expanded this, right? And then when you pick the left hand side, you realize that k squared is also 2p minus k. So after simplifying this, you get this, right? So you're going to replace k squared by 2p minus k. So let's do that. Replace k squared by by 2p minus k. Minus k plus 3k gives us 2k. So I left with this. We can factor out the 2 because we're trying to check if this is even. Then we say this is 2r with r being equals to that. You say, right? Which is an element of an integer. Then we say thus p of 1 is also true, hence p of n is true for all elements of a natural number. Now we have these ones of inequalities, right? Let me check if I think there's also all right. Let's look at these ones of inequalities. Now we have these ones of inequalities, right? If we look at these ones of inequalities, they say use PMI to prove that 2 to the n minus less than 2 to the n less than n factorial for n greater or equal to 4. Now we're dealing with inequalities. So the inequalities, it's going to be different a bit, right? We're going to let these ones, actually it's going to be the same from everywhere up until the deducing part. Everything is the same. You do the same thing with the one of divisibility, right? You let p of n be the statement, copy that as it is. Then you start plugging 4 because they say this is greater or equal to 4. You plug a 4, you say, right, it's greater or equal to 4. Then after plugging a 4, you get that this is equal to 24 on the right hand side, and then on the left hand side is 16. And indeed 16 is less than 24. Hence p of 4 is true. Then we assume that p of k is true for some k greater or equal to 4. Then we just replace our n by k. Then we deduce that p of k plus 1 is also true. We replace our k by k plus 1. Then when you come to proving this, guys, we're going to pick this from assumption. We're going just to take our assumption. Remember, our assumption is 2 to the k, which is less than k factorial. So always we're going to be multiplying by this base both sides. The next step we multiply by that base both sides. You see it right now. Then we multiply by that base both sides. Then we arrive on the left hand side. Left hand side we have already arrived. Then to arrive on the right hand side, remember these signs are not going to, they will never face that side. This sign will never face that side. You must always keep in mind. It's either it's like this, or it's like this, or it's like this. These are the only three that you can use. And I'm going to show you how to use them. We are trying to manipulate to this k plus 1 or k plus 1 factorial. And we have 2k factorial. Since we have 2k factorial and we're dealing with a factorial, we are only going to manipulate the number. If there was no factorial here, we're going to manipulate the entire thing. You say, right? If it's 2k factorial, we'll manipulate the number by what we are given here. We have k, so it's like this actually. You see this, right? Plus 1. But our k is greater or equal to 4. So we're going to put what here? 4. But you're also going to say greater. So we keep the sign like that. Then we will substitute our 4 by k. and k is greater or equal to 4, and then this one changes to greater or equal to 4. This one, guys, let me show you this. Let me erase here. First thing, we know that this ones won't change, right? The second thing that you need to know, this second one, when you're manipulating, will always be greater. If our signs are like this, right? The sign will always be like this. Remember, when I say greater, I'm comparing this one to the previous one. So I'm just saying greater. You see, right? Then the sign will always remain like this here on the second one. This one here will change based on what does our condition say. Does it say greater or equal to, or does it say greater? If the condition said greater, this would remain greater. You see, right? But the condition said greater or equal to. You see, right? Then this will replace the 4 by k. So this is what you must keep in mind. Let me repeat this. We have 2k factorial. We're going to keep the sign first. Then we plug the number that we are given, the condition of the number that we're given, then we add the 1 to that number. We replace 2 by that number, then we add the 1. If this was a 6, we're going to say 6 plus 1. You see, right? And then, when we come here, we're going to replace the 4 by k. And we know that they say that it's greater or equal to. So this will write greater or equal to. And k plus 1, k factorial, is the same thing as k plus 1 factorial. You see, right? And then we have arrived to the right hand side. Then we'll say thus, p of 1 is also true, hence p of n is true for all n greater or equal to 4. Any question here? If there's no question, I'll just assume that you guys understand, right? Now let's go to the questions based on this. Yeah, now we come to, okay, let's come to the one of factorials first, right? This one is different from the factorial one. Now we come to this one of factorials, right? We're given this. They say that we are given this. They say that 3 to the n is less than n factorial for all n greater than 6. You see, right? Then first we let p of n such that we copy that inside statement. Then we check 7 because n is greater than 6. It means that n must be starting from 7. We check 7. We get that the left hand side is 2, 1, 8, 7. The right hand side is 5 or 4. And this is true. 5 or 4 is greater than 2, 1, 8, 7. Hence p of 7 is true. Then we assume that p of k is true for some k greater than 6. Then we have this. We just replace n by k. You see, right? The left hand side. Then from here we deduce, this thing is kicking me out. Then from here we deduce that p of k plus 1 is also true. Then we're just going to replace k by k plus 1. You see, right? Then from here, we take it from assumption. Our assumption was saying 3 to the k less than k factorial. Then we multiply both sides by the base. You see, I said that the first thing you do, multiply by the base, then you're going to arrive to the left-hand side. You see, right? Then we arrive to the left-hand side. Then after arriving to the left-hand side, we can now manipulate the 3. The 3, when we want to manipulate it, we say Remember I said that this one will always be greater if this is greater, right? We'll always follow this sign first. And remember here I said that if the signs are like this, they'll never turn and face the other side. Now we say this, replace this 3 by this number, we add 1. Because there they had said that k is greater than 6. So we're taking this number, we add the 1. We replace that 3. You see right? Then we replace this number by k. Because the condition we had said it's greater only. We won't put greater equals to there. We'll just leave it as greater. And this is equal to k plus 1 factorial. Do you see this? Then the conclusion is always the same, guys. I've been preaching this conclusion. Make sure you write it there. So, is there any question here? So if there's no question, we can come to this one. Then we let p of n such that 2 to the n is greater than n squared for all n greater than 4. Then we start by 5, plug in 5 because indeed this is greater than 4, right? Meaning that n starts from 5. We get that the left hand side is 32, right hand side is 25, which makes sense. It's true. Hence p of 5 is true. Then we assume p of k is true for some k element of a natural number. Then we have this, so replace n by k. Then we deduce p of k plus 1 is also true. We replace k by k plus 1. See, right? Then from assumption, we take this. We multiply both sides by the base. Same thing we do always. Then we arrive to the left-hand side there. Then once we manipulate the right-hand side, remember there's no factorial anymore here. So for us to manipulate this, we must expand it in this manner. This is the only way, right? Then remember the right-hand side there is saying this. The right-hand side is saying that this is equal to k plus 1 all squared, and this is the same thing as, so for you to know if you're doing the right thing, you need to expand this to 2k plus 1. Then we check. We needed k squared. Already we have k squared, right? So yeah, let's check from this one. After expanding the first one, we already have k squared. We don't need this. So we're going to expand this to k squared plus k times k. Then this one we replace it by 4. This will be greater because this is greater. So this will be k squared plus 4k. And we don't need 4k, we need 2k. Remember the right hand side is like this. We don't need 4k, we need 2k. So we expanded the 4k to 2k plus 2k. And then we need this. Now we got this. We don't need the 2k, this other 2k. We need a 1. And the only way to get to that is if we plug 4 there. We get an 8. So this will remain great. So this one will be greater than this. Or this will be less than that. So that's how you compare, right? Compare to the previous one using this sign. Now, we know that 8 will always be greater than 1. So the sign is still applicable. You see that the sign started by looking this side. It will never look at the other side. You see, right? So now we arrive to the right hand side. You can just easily change this to k plus 1 all squared. Thus, pk plus 1 is also true. Hence, p of n is true for all n greater than 4. Any question? So I think if there's no question, right, we can stop here. I think we can talk about having another session late. Let me just give you a break to breathe. Then you guys can suggest the other time we should have a session so we can look at this other part. We can look at this part of binomial expressions, expansions, binomial theorem, all these. We can look at all these, right? The triangle inequality, Pascal's triangle. Also, we can look at the binomial theorem, to how is this theorem computed, right? We can look at this theorem. Then we look at expanding. Yeah, I think you can decide there in the group what time can we have another class. Let me just share this guide there so that you can look at the things we're doing.